Let's start out with a brief history of the discovery of electronics. This not only gives us a timeline of how things developed, but it gives us some insight into the nature of electricity. So if we go all the way back to the ancient Greeks around 600 BC, a Greek mathematician by the name of Thales of Miletus is credited with discovering that if you rub amber with wool, that it gains magnetic properties. It will attract small items such as dust and feathers or chaff. And he thought that amber must be alive because it was able to make things move. Now, electricity remained pretty much a curiosity for parlor tricks or whatever for quite a few years, until 1600, when William Gilbert published a treatise titled On the Magnetic Bodies and That Great Magnet, the Earth, where he noted that the magnetism of amber was different from the magnetism of lodestones, and he coined the term electricity to describe this. Electricity comes from the Greek word for amber, electron, spelled with a K. In 1729, a British astronomer by the name of Stephen Gray was experimenting with electricity that he created by rubbing a glass tube with silk. He had a cork in the end of the tube to keep it dry, and although rubbing a cork will not create electricity, when he had that cork in a glass tube that he had rubbed with silk, the cork did become electrified. He stuck a fir stick into the cork and found that the electricity carried all the way to the end of that stick. By the next day, with the help of a friend, he had taken a oily hemp thread and caused the electricity to be carried all the way from his balcony down to the courtyard below. And after some more experiments, he found that it could go around corners and seemed to be unaffected by gravity. So since he can make electricity go from one place to another, he speculated that electricity must be some kind of fluid. And the term electrical fluid became part of the lexicon and was used to describe electricity up until the early 20th century. Gray had corresponded with Isaac Newton's assistant, John de Galilei, and had been telling him what he'd discovered. Gray discovered that some materials carried electricity better than others, and other materials would not carry it at all. In fact, he used silk threads as an insulator. And de Galilei actually came up with the terms insulator and conductor to describe those things that would carry electricity or would not. In 1736, Charles Francois Dufay noted that when you rub amber with wool, it becomes electrified. That was already known. And also if you rub glass with silk, it becomes electrified. That was already known also. But he noted that if you rub two pieces of amber with wool, that they will repel each other. And if you rub two pieces of glass with silk, they will repel each other. But if you take a piece of amber rubbed with wool and a piece of glass rubbed with silk, that they will attract each other. So he speculated that there must be two types of electricity with opposite properties, and he named them resonance electricity for the kind of electricity you got from rubbing amber with wool. Amber is fossilized tree resin. And the other type he named vitreous after the Latin name for glass. So he speculated there are two types of electricity, resonance and vitreous, with opposite properties. In 1745, Edvald Georg von Kleist tried to store electricity in a medicine bottle filled with alcohol. He put a nail through the cork and touched that nail with an electric generator, which was probably a sulfur ball that he spun with a crank. And he noted that when he cradled that bottle in his hand and touched the nail with the other hand, that he got a substantial shock. Peter von Mussenbruck tried to repeat his experiments using a glass of beer and noticed that it only worked when he cradled the glass in his hand. So his hand actually became part of this device. William Watson discovered that it worked even better if you wrapped tin foil or lead foil around the glass instead of using your hand. What this eventually evolved into is what we now call the Leyden jar. The Leyden jar is a jar, which is made of glass, which is lined on the inside and the outside with tin or lead foil, and the lid has a metal post in it with a chain reaching down to contact the inner cup. And the post has a ball on the top because they found that the electricity mysteriously leaked away if there were sharp points on the top of this post. So putting electricity into the post would store electricity in this jar. Now, Benjamin Franklin, around 1750, discovered that if you put resonance electricity inside the Leyden jar, that it would develop vitreous electricity on the outside. And that if you put vitreous electricity on the inside, it would develop resonance electricity on the outside. And that if you touch the post to the outside foil with a piece of metal or a piece of wire, that the electricity would disappear. So Franklin decided that maybe there's only one kind of electricity, and when I put resonance electricity inside, I get a greater quantity on the inside and a lesser quantity on the outside, and that's what makes there seem to be a difference on the inside and the outside. So there's a greater quantity inside and a lesser quantity outside, and when he touched a wire from the post to the outside cup, the greater quantity would flow to the lesser quantity until they were equal. And of course, likewise, if you filled it with vitreous electricity, you would have more on the inside, less on the outside, and if you touched them together, it would flow. Except if he was correct that there's only one kind of fluid, let's say that the resonance was the greater quantity, you fill it with resonance electricity, you have more on the inside, less on the outside, and then if you touch it with a wire, the electricity would go from the post to the cup until they equalized. Or if I brought vitreous electricity up here, it was really sucking electricity out, creating a greater quantity on the outside than the inside. And then when I touch them with the wire, it flows from the outside to the inside until they were equal. What Franklin couldn't tell with the tools of the time is which was the greater quantity and which was the lesser quantity. There was no way to tell. You couldn't see which way it was flowing, and you couldn't really measure which was which. You could just tell that one was greater than the other. William Watson decided that the greater quantity should be called positive electricity and the lesser quantity should be called negative electricity, but yet with the tools of the time they couldn't tell which was which. By this time it was obvious that lightning was electricity. When you played with static electricity, you got small sparks that looked like tiny bolts of lightning accompanied by a clicking sound, and lightning looked like big versions of these little sparks and was accompanied by a big boom. They must be the same thing. And also, it was obvious that lightning went from the cloud to the ground. You could see it. So, if you could extract some of the electricity from a cloud and see if it's vitreous or resonance, you could see which is the greater quantity. In 1750, Benjamin Franklin proposed an experiment of sticking a metal rod up on top of a hill into a cloud, putting a Leyden jar at the bottom, and extracting electricity, and seeing, one, is there electricity in clouds, which would support the fact that lightning is electricity, and if you could get that electricity and see if it's vitreous or resonance, now you know which is the higher quantity and which is the lesser quantity. In May of 1752, Charles Francois Dalibard, who had been in communication with Franklin, performed his experiment by attaching a 40-foot-long metal rod to a stone building on top of a hill and putting a Leyden jar at the bottom. He left it alone for a while, came back, and found electricity in the Leyden jar. And the electricity was vitreous, proving that the higher quantity, which was in the clouds, was vitreous electricity, or vitreous was positive electricity. 2 months later, unaware that Dalibard had beat him to the punch, Franklin performed his famous kite experiment and also extracted electricity from a cloud, and it was also vitreous, supporting what Dalibard had already discovered. Some historians doubt that Franklin actually performed his kite experiment, and their reason for doubting that is because he lived to tell about it, when several people who tried to repeat his experiment were struck by lightning and killed. Franklin himself said you don't need a thunderstorm to perform the experiment, but he said that after at least one person had been killed trying to repeat it. He did write to friends talking about the experiment, and Joseph Priestley did publish that, and there are no contemporary disputes that he did his experiment, and I believe he actually did it. I just don't believe he actually flew his kite in a thunderstorm. He never proposed that, as far as I can tell, and you can extract electricity from any cloud. In fact, the Mythbusters, trying to repeat Franklin's experiment, were able to extract electricity from clear air, so you don't need a cloud at all. In 1781, Henry Cavendish, who is best known for discovering hydrogen, developed some rules for the flow of electricity based on the differences in abundance. So we have a greater abundance here and a lesser abundance here. It's going to flow from that greater abundance to the lesser abundance, and he developed the rules for how much flow there is, depending on how much difference there was in abundance. The Royal Society did not publish his works, and so he is not known widely for his work in electricity. Also in the 1780s, an Italian physician by the name of Luigi Galvani noticed that when he was dissecting a frog's legs with metal instruments, that he could extract electricity out of the legs and that the muscles would twitch. And so he speculated that there was electricity in the frog's legs. Later, an Italian physicist named Alessandro Volta was repeating his experiments and noticed that it only worked when he was using dissimilar metals. So he thought that maybe it was the metals reacting with the fluids in the frog's legs that were producing the electricity and not the frog's legs themselves. To test his theory, he set up a stack of different kinds of metal using copper and zinc. He separated these metals, copper and zinc, by paper that had been saturated in brine and stacked them up and found that they did produce electricity. And the more he stacked up, the greater was the force between the positive side and the negative side. When Volta connected a conductor between the positive and negative side, he got a steady flow of electrical fluid from the positive to the negative. And for the first time, we were able to have sustained electrical currents. Today, we call this the battery. A battery, or voltaic cell, is made with dissimilar metals that are reacting with each other through some kind of acid or base solution. And this reaction causes a greater abundance of electricity on one side than the other. Today we know that it's actually a greater abundance of electrons compared from one side to the other. Historians credit Volta's invention as allowing portable electronics, but that is quite an understatement because with Volta's pile, for the first time, we could have sustained electrical currents, which led to discoveries such as electromagnetism, and which allowed us to make motors and generators and solenoids or electrical actuators, and also allowed us to develop modern electronics because most electronics, if you discount motors and light bulbs, require a battery to operate. In fact, anytime you plug something into the wall, that power goes to what's called a power supply, which simulates a battery. In fact, we used to call power supplies battery eliminators. And just about everything requires either a battery or a simulated battery to operate. So without Volta's invention, modern electronics as we know it could not have been developed, and electricity could not have ushered in the modern world as we know it. In 1820, Hans Christian Ørsted was demonstrating Volta's pile when he noticed that a magnet placed near the wire that was connecting the two ends of the pile pointed towards the wire. And when he moved the compass next to the wire, that the needle lined up perpendicular to the wire. And when he reversed the pile, that the needle flipped its direction. So he noticed that when there was current flowing through the wire, that there was a magnetic field around it. And when he stopped the current by breaking the circuit, that the magnetic field disappeared. So Ørsted discovered the relationship between electricity and magnetism. What he discovered was that when there's current flowing through a wire, there's a magnetic field around that wire. He also discovered that when you pass that wire through a magnetic field, while that wire is moving through the field, it produces an electric current. In 1827, Georg Simon Ohm published a book on electricity that in part restated what Henry Cavendish had already worked on, and he improved on his work. It was already known that some materials conducted electricity better than others, and Ohm called this property resistance. In other words, if something conducted better, it had less resistance, and if something conducted worse, it had more resistance. And Ohm developed a formula based on the electrical force between the ends of a voltaic pile and the material that the wire was made of connecting the two, and how much resistance it had, and predicted how much electricity would flow from one end to the other, which was called electrical current. And this formula is now known as Ohm's law. In the early 1830s, Joseph Henry in America and Michael Faraday in England were both experimenting with electromagnets. What they did is they took a voltaic pile, ran a wire from it, and wrapped coils of this wire around an iron bar. The coiling of the wire and the presence of the iron concentrated the magnetic field and improved the quality of the electromagnet. Henry noticed that when he disconnected the wire that he got a little spark. And he thought that, well, we have electrical current flowing through the wire, it must have momentum, and when I disconnect it, that momentum causes it to jump across the gap and make a spark. Later, Henry realized that it wasn't momentum of the electricity that was causing that, but the magnetic field around the coil. Remember that when you have electricity going through a wire, you get a magnetic field, but if you move a wire through a magnetic field, you get electricity. And he realized that when he broke that connection, that the magnetic field collapsed, and the moving magnetic field generated a new electricity in the coil, and that is what created enough energy for the electricity to jump the gap and make a spark. Now, Henry and Faraday also noticed that if you put another coil of wire near the first, that when you broke the connection in the first coil, that if you had a small gap in the wires connected to the second coil, you would get a spark across that too. And of course what they realized was that the magnetic field around the first coil was collapsing around the second coil, generating electricity in the second coil. When you have this electricity generated in one coil by itself, we call this self-induction. And when you have two coils next to each other and one coil induces a current in the other coil, we call that mutual induction. Faraday and Henry were both doing these experiments around the same time, but the scientific community decided to give Henry credit for discovering self-induction and Faraday credit for discovering mutual induction. Today we call this device a transformer, where we can have a changing voltage on one side causes another voltage in the other side. And we can actually change the voltages where if we have a lot more coils or turns in the second coil than we do in the first, that the voltage will be proportionally higher. Or if we have less coils or less turns, the voltage will be proportionally lower. And we can use this to step voltages up and down. And this was very important for power distribution because at very high voltages, we can send electricity very efficiently over very long distances. But that's too high to work with, it's too dangerous. So then we can use transformers to step it back down to safer voltages to be used. Now we come to 1837, when Samuel Morse did not invent the telegraph. Actually, historians today credit the telegraph to Joseph Henry because he developed a little device where he had a switch in his office, a voltaic pile, a set of wires going over to his home, and a bell in his home where he could flip the switch and ring the bell at his home. And so he is credited with inventing the telegraph. And actually by the time Samuel Morse came along, there were telegraphs being used all over the world. But they were fairly cumbersome devices, trying to make them usable by people with low skills. For example, one type had buttons labeled with letters of the alphabet. You press one of those buttons and turn a crank until it aligned with that button. And on the other end, a pointer would turn around with the crank and then point at a letter of the alphabet, and you could send messages that way. Morse developed a contraption which wasn't much better, but eventually he realized that you don't need to have all these contraptions. Why not just have a switch at one end and an electric clacker at the other end and train the operators to use a code where you could tap out a code on the switch and then listen to the clacker at the other end and just interpret what was coming through. So Morse's actual contribution to the spread of the telegraph was how he simplified it to nothing more than a switch, we call a key, on one end, and an electromagnetic clacker on the other end. Another thing that Morse did is he discovered you did not need two wires. You could use one wire for the telegraph and use the earth itself as the return. So even though Morse actually uninvented the telegraph by simplifying it to nothing more than a switch and a clacker, his telegraph is the one that spread throughout the world. In 1838, Richard Laming proposed that certain chemical reactions could be explained if electricity consisted of individual packets of charge or particles. In 1845, Gustav Kirchhoff developed rules that explain how electrical force, or voltage as we know it now, is distributed through a circuit. He also developed rules for how current is distributed among multiple circuits. These are now known as Kirchhoff's voltage law and Kirchhoff's current law, and are equally as important to Ohm's law in describing how electricity works in a circuit. Now, by the mid-1800s, it had already been noted that if you pass enough electrical current through a conductor, that current will glow, and the more current you get, the brighter it glows. And so this led to the quest to develop an electrical light bulb. Many people were trying to develop an electric light, but the problem was that either things would melt if they got hot enough to produce enough light, or if they didn't melt, they would combine with oxygen in the air and burn up. Joseph Swan of England and Thomas Edison of America were the ones that discovered that the solution was finding something that would glow but not melt, and encasing it in a glass bulb and sucking the air out so that it could not react with the air. Thomas Edison developed a way of mass producing the light bulb, and for that he gets credit for inventing it, although there were other people working on it, and Joseph Swan should get equal credit to the invention of the light bulb. Around 1862, James Clerk Maxwell proposed that light was made up of waves of electricity and magnetism that were interacting with each other. This theory was accepted by the scientific community at the time, but he also proposed that there were waves of electromagnetism that we could not see that had longer wavelengths and shorter wavelengths than light. Those theories were not accepted by the scientific community. In 1874, Carl Brown discovered that certain crystals would conduct electricity in only one direction if you made contact with those crystals with a piece of wire and that contact was imperfect. Later on, he patented the crystal rectifier. This device was the earliest predecessor to the transistor. In the early 1870s, David Hughes noticed that carbon granules sandwiched between two electrical plates would vary their resistance in response to sound waves, and invented the microphone. He decided not to patent this, but made the microphone a gift to the world. In 1876, Alexander Bell and his assistant Thomas Watson were trying to develop a telegraph that could send multiple messages over a single telegraph wire at the same time. While they were experimenting with this, they noticed that their apparatus responded to sound, and realized that with modification, this could be used to carry voice over telegraph wires. Bell's device consisted of little more than a diaphragm that would pick up sound waves with a magnet attached to it, and as that magnet moved in response to sound waves, its magnetic field would move back and forth across a coil of wire and generate a current that he called voice-shaped currents in that wire. And at the other end, he had another coil of wire, and that magnetic field would be getting bigger and smaller in response to the changing currents and would attract another magnet with diaphragm back and forth. So speaking in one end would create these voice-shaped currents, which would then cause the other end to vibrate, and it was able to carry sound from one end to the other. Bell's telephone was virtually useless because you had to yell in one end and listen carefully in the other, and it couldn't be used over great distances. However, in 1877, Thomas Edison rediscovered what David Hughes had already discovered about carbon granules between plates of metal, and he reinvented the carbon microphone. And by replacing one end with a carbon microphone and putting a battery in the system, now we have a current running through here constantly, and speaking into the carbon microphone causes that current to vary according to the sound waves hitting the microphone. Edison's carbon microphone was many, many times more efficient than Bell's microphone receiver that he had there before. This finally made the telephone practical, and up until the 1960s or 70s, telephones were still made this way. In fact, even today, the modern telephone system will still accept this kind of telephone into its system. In 1878, David Hughes was experimenting with an induction balance, which is similar to a modern metal locator, which uses coils of wire to detect metals by the change of the inductance of that coil in the presence of metal. While he was turning this induction balance on and off, he noticed that a telephone across the room was receiving clicking noises through the air, if that telephone was connected to its battery with a loose connection. He packed this up and took it to the Royal Society and told him that he had discovered the invisible light waves that Maxwell had predicted existed. However, the Royal Society dismissed this as mere induction, which was already known. Even though it was carrying over great distances, they thought it was the same thing that Henry had already been credited with, and it was just simply the magnetic fields that were interacting, but not some kind of invisible waves going through the air. However, in the late 1880s, Heinrich Hertz was able to produce these invisible waves in the laboratory, and he proved that they were waves because he was able to measure their wavelength, and he was able to make them reflect and refract just like sound waves or light waves. So Heinrich Hertz is now credited with discovering radio, and David Hughes is virtually unknown. In 1894, George Stoney repeated Lamming's proposal that electricity must consist of individual packets of charge or particles, and he called these particles electrons after the Greek word for amber. In the early 1890s, Guglielmo Marconi improved on Hertz's apparatus for producing radio waves and was able to send radio waves over great distances. And by turning his transmitters on and off with a Morse code key, he was able to send messages using Morse code. In 1895, Westinghouse built the first hydroelectric power station in Niagara Falls using generators designed by Nikola Tesla. At this time, Edison was distributing electricity over short distances using direct current. But Tesla's generators made alternating current, and with alternating current that could be sent through transformers that I described earlier, stepped up to extremely high voltages and delivered efficiently over long distances, and then stepped back down to useful voltages at the end. In the early 1900s, John Fleming noticed that when you used a light bulb, the glass itself would darken, and he thought that something was streaming away from the hot filament and coating the glass. He experimented by putting a cylinder of metal around the bulb and attaching an electrode to it, and found that if he put a high voltage across here with the positive on the electrode and the negative on the filament, that he could get an electric current to flow through the vacuum to that plate from the filament, and that if he reversed that battery, the electricity would not flow. So he developed a vacuum valve, or diode as we call it today, that allows electricity to flow in only one direction. In 1904, Ernst Alexanderson developed generators that worked at very high frequencies, and by putting an antenna on these, he was able to produce radio waves. These were different from Marconi's radio waves because Marconi's waves were very chaotic. They were a whole bunch of frequencies all mixed together, much like white light is all the different colors of the spectrum. Where Alexanderson's transmitters produced a single frequency, which was much like a pure color of light, like pure red or pure green or pure blue. And this allowed the possibility of sending multiple radio signals at the same time in the same geographic region using different frequencies. In 1906, Reginald Frizenden attached a carbon microphone between the antenna and one of Alexanderson's transmitters and was able to transmit voice over radio for the first time. In 1907, Ernest Rutherford developed a new model for the atom where we have a nucleus surrounded by electrons orbiting the nucleus, much like planets orbit the sun or the moon orbits the earth. In 1913, Niels Bohr modified this model to the familiar model we have today, where we have a nucleus of protons and neutrons with the electrons orbiting at different energy levels. This model is pretty much obsolete, but it still explains some things that atoms do and electrons do, and so we use it to make those explanations. In 1907, Lee DeForest made a modification of Fleming's valve where he wrapped a grid of wire between the filament and the plate, and by putting a large voltage across here, positive to the plate and negative to where the filament was, he got a stream of electrons going from the filament to the plate, and so he had an electric current flowing, and by putting a small negative charge on this grid, he could cut off or control the flow of the electricity going from the filament to the plate. So now we had a small signal here able to control a much bigger flow of electricity, and we were able to have electronic amplification. So for example, we hook up a microphone to this grid and a speaker in the circuit over here, and talking into the microphone would make the speaker produce a louder sound. One problem with this type of amplifier is that they tend to feed back and oscillate. You've heard this in auditoriums when you hear the feedback and squealing from the PA system. Scientists noticed that they can make these oscillate at very high frequencies and produce radio waves much more efficiently and at much higher frequencies than the Alexanderson generator-based transmitters. Like Alexanderson's transmitter, these transmitters produced a single frequency of radio waves, which was like having a single color of light. If you can imagine using a Marconi transmitter, which was like flooding the area with white light, you could only send one message by flashing that light. But with these types of transmitters using these types of tubes, you could have something like a red light sending a message and a green light sending a message, and there were two completely separate messages that you could filter out on the other end. And so radio filters could be used to send different messages in the same geographic area at different frequencies. Because of that, the Marconi transmitters were quickly outlawed, and these kind of transmitters became the norm. Now that we had these types of transmitters that could transmit on a single frequency and we could use filters to filter out the ones we didn't want, the problem was tuning the receiver was a rather arduous task and took a certain amount of time, and so you couldn't easily change a receiver to pick up one frequency and then move it over to pick up another frequency. In 1918, Edwin Armstrong invented a new kind of receiver that you tune once to a single frequency, and then another circuit that was very simple was used to take the radio frequency you wanted to listen to and convert it to the frequency that your radio was tuned to. This was called the superheterodyne receiver. And so now you had a receiver that you could easily tune from one frequency to another by simply retuning the circuit that changed the frequency you wanted to listen to the frequency that your receiver was tuned to. Tuning that very simply would change the whole radio system to pick up the signal that you wanted to pick up and reject the others. In the summer of 1921, a 14-year-old Idaho farm boy by the name of Philo T. Farnsworth was studying electronics at his local library and experimenting in his attic with what materials he could find. He was wondering how it might be possible to send pictures over radio. One day while plowing his field, the back and forth motion he was making with his plow gave him an idea. The idea he came up with was to use a modified Crookes tube called a cathode ray tube. This had an apparatus in one end called an electron gun that would shoot a stream of electrons at the other end. This stream of electrons could be focused and steered with electromagnets on the outside of the tube. Farnsworth's idea was to put a plate with photosensitive material on it at this end of the tube and use a lens to focus an image onto that plate. Wherever more light struck the plate, it would become more conductive, and where less light struck the plate, it would be less conductive. As the electron beam was steered back and forth and up and down across the plate, when the electron beam struck a place that had more light, there would be a greater electrical current, and when it struck a place with less light, there would be less electrical current. And this current would be taken out of the tube, out the back, and sent off to be processed. So now he has a stream of electrical current that is stronger when the electrons are hitting a bright part of the plate and weaker when the electrons are hitting a dimmer part of the plate. At the receiving end is another cathode ray tube that also has an electron beam that is focused and steered by electromagnets, and this beam is synchronized with the beam in the first tube. At the other end of the tube, it is coated with a material such as phosphorus that glows when the electron beam hits it, and it glows brighter when the electron beam is stronger and glows less when the electron beam is dimmer. These two beams are synchronized so that they go back and forth and up and down together, and as we get more current from this tube, we get a brighter spot in this tube, and as we get less current from this tube, we get a dimmer spot in this tube, and so the second tube paints an image that recreates the one in the first tube. It took a number of years for Farnsworth to perfect this, but he eventually tried to license it to RCA. RCA sent an engineer named Vladimir Zworykin to examine Farnsworth's equipment, and when Farnsworth refused to sell his patent outright to RCA but only license his idea, Zworykin simply stole it and was credited with inventing television. In a subsequent lawsuit between RCA and Farnsworth, it was proven that Farnsworth did indeed come up with this idea when he was only 14 years old, and the courts found in his favor. And so Farnsworth is now credited with being the inventor of electronic television. In 1933, Edwin Armstrong developed a new kind of radio transmitter. Transmitters of the time used amplitude modulation, which means that the power output of the radio transmitter was varied in response to the vibrations of a microphone. Armstrong invented frequency modulation, where the output frequency was varied instead of its power output. This would be like taking a pure red light and making subtle variations in the shade of red that it put out. The advantage of frequency modulation is that it's much less susceptible to noise than amplitude modulation and made possible broadcasts of high-fidelity music. In 1947, John Bardeen and Walter Brattain, working for AT&T Bell Laboratories, made a modification of Brown's rectifier diode that had 3 connections, and if you made small variations in voltage at one connection, it would make big variations in the current traveling between the 2 other connections. Later, these transistors could be made cheaply on a single piece of silicon using photographic techniques. Bardeen and Brattain's boss, William Shockley, is often credited with inventing the transistor, but he actually did not participate in the work. In 1960, a group at Fairchild Semiconductor decided if I can make one transistor on a piece of silicon, why not make multiple transistors and interconnect them? So they developed a photographic technique of making multiple transistors, diodes, and other components on a single piece of silicon and developed the integrated circuit. Of course, today we have integrated circuits that have millions of transistors, and this has made the modern miniaturized electronics we have today possible. In 1961, James Baird and Gary Pittman were working with a modified version of Brown's rectifier diodes called a tunnel diode, and noticed that it was emitting infrared light when it was conducting. They developed this into an efficient infrared emitting diode. In 1962, Nick Holonyak invented a visible red light-emitting diode, and later green light-emitting diodes were developed. These were mainly useful as indicator lights, but they were much more efficient and longer lasting than incandescent lights. Over the years, more efficient and brighter light-emitting diodes were developed. However, for many years, the only ones that were practical were red and green. If a practical blue LED could be invented, then red, blue, and green LEDs could be combined to make white light. Practical, commercial blue LEDs came out in the early 1990s, and in 1994, Shuji Nikamura developed the first high-brightness blue LED. Now with red, blue, and green LEDs, white light can be produced with LEDs. This is usually done in video displays using organic LEDs or OLEDs. White LEDs used for area lighting usually use deep blue highly energetic LEDs that shine onto a phosphor that converts the blue light into white light. This history is certainly incomplete, but it does cover the major inventions throughout the years that brought us modern electronics as we have them today. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe and hit that gray bell also, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocatomy.net, you can go to patreon.com/join/vocatomy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.